I've been your host, Kris Jenkins. This has been Developer Voices with Zhong. Thanks for listening. And the Lambda architecture was proposed as a solution to Twitter's big urgent problem. You have these two roles you need to fill. You've got a huge set of historical data that needs to be queried in all the usual ways, but then there's this much smaller set of live data that's really urgent and has to be processed right now if it's to be of any value. And there's a mismatch between those two kinds of data. They have different storage requirements, they have different access patterns, and of course, they have different performance constraints. Plus, there's the extra problem that the new data is going to become old data. So eventually, every piece of data you have will live in both of those roles. It can be very difficult to deal with because you can't optimize one without sacrificing the other. And the Lambda architecture proposed this solution. Accept it. You're going to have two different data systems. And what you have to do is build them optimized for each use case, and then do all that difficult integration work that makes those two systems appear like they're one system. It's very hard. I remember it taking a long time, but they did it. But what if you could get all that integration, both of those systems neatly coupled together, off the shelf? It seems to me that that's the question being asked by this week's guest, Zhong. And his answer is the recently open source database Proton. Well, if that's his answer, I have questions. What's a database like that for? What does it do well? How does it work? And how are you making that difficult integration piece simple enough that I can rely on it, but transparent enough that I can forget about it? That's the trick. I suggest we find out. I'm your host, Kris Jenkins. This is Developer Voices, and today's voice is Zhong. Joined today by Zhong. Jove, how are you?
I'm doing good. Hi, Kris. So glad to join this podcast.
I'm glad you've joined us. You're in a world with a lot of people competing to try and solve this problem, right, of streaming data. And it seems to me that everybody has a slightly different way of solving the problem, and those architectural decisions that they make play out in different and interesting ways. So I want to pick your brains on the architectural decisions you've made and how it plays out in the system Proton that you've ended up co-designing, right? But before we get into that, I think we should try and ground ourselves in what's this for? What's an end user going to actually use this for?
Yeah, sure. Yeah. So Proton, I would say for people who are not that familiar with the idea of stream processing, you can just consider this is a next generation ETL. Even I suppose people know what is ETL. So you want to move data from A to B, and you want this as fast as possible, no latency. You don't have to wait for the next batch, say next 1 day, next 1 hour. Whenever there's something happening, for example, there's a new order coming, there's a new people click your web page, there's a person being attacked, a server is going to be OOM.
Like security,
Those information can be sent to the system in the almost zero latency, and you can apply some alert, you can have some automated actions. So this is really good for build a real-time or streaming ETL. So beyond that we also really is a true streaming processor. So meaning that is it's not just fast enough, it's also have this stateful processing. So the difference that is we can do some stateful processing, such as say I can count every 1 second how many click for that particular page. Then I accumulate a state within that 1 second or 1 minute. Even you can do some fancy things such as this session window. Whenever a signal, meaning that session start and the session end, and we keep this session window, for example, when the user log in, do a bunch of action until they check out or log out, this is a session. The session window can be as long as, say, 2 hours, or can be just 5 seconds if the person is not patient enough.
It's the digital equivalent of someone comes into your shop and you want to kind of understand them until they leave, right?
Yeah. So all those simple transformation or filtering, or those sophisticated stateful processing, all those are in the category of stream processor. So some of the big players in this space, for example, like Apache Link. And there's some other vendor, as you briefly mentioned. That it's not a new space, but still at early stage because people are really want to get things more real time. They may still struggle on the batch side, but more and more people want to get to the next chapter, which is streaming. So this idea of stream processing analytics is really a new thing, and people really want to try different solutions.
Thing that interests me, and I keep coming to I want to hear about everyone because everyone in this space is scrabbling to come up with the ideal solution or the solution that's optimized for a particular subset of that market. And everyone has a large piece of the answer, and everyone's saying that they've got the whole of the answer, and I just kind of want to explore it, right?
Yeah, exactly.
But first, I'm going to pick you up on a word, a specific. I'm going to nitpick your word that you said. It's a true stream processor. You said.
Yes.
What's a true stream processor?
This definition of stream processor is really about how to handle the streaming data in a meaningful way, right? The streaming data is the data you constantly get. So you get not just batch by batch. You always get new data all the time. And you also want to process data in the streaming way, not in the batch way. So more like a common or naive solution that is you always get the data from your OLAP system. There's a lot of OLAP system. I guess the market of OLAP system is even busier than our streaming processing market. But anyway, you can always put the data into your OLAP system and you can query it every 1 second. Right? Then if your system is powerful enough, you get quite nice dashboard or alert with the limitation of you get this every 1 second or every 1 minute. I think most systems don't really happy to support per second query because that's too much, too frequent. And what is worse, that is, imagine you want to get, hey, what's my revenue this month? And you want that number update every second or maybe every minute. Then if you are using OLAP system, then you query this every 1 second or 1 minute, but you are wasting a lot of resource, right? Because the number you get last time, maybe it's, say, 10,000. And between these two queries, you might get a few transactions and you might get 10,000 and 200. But because you are run this as a batch query, you end up with query all the data over again, even that's a very small incremental thing, right? So this is the common, we call real-time solution. And for the streaming processing, we have this state. So we know what's the last time we query is this, say, 1,000. Then there's some new event. We know the delta. So we can give you we get the delta combining with the previous result. We'll give you the new thing. And what is more interesting that is usually this streaming processing is a long-running process. So you only run your query once, and it never ends until you cancel it. Even the server start, restart, or scale out, usually the system can still keep the state and resume what is left until you explicitly cancel it. So back to that previous example, that is, you want to know what's the live number of this month's revenue, and you just run one single query, something like select some amount from stream. And that streaming processing will keep giving you new results whenever new data is available. So you are happy to render this Nestle, or you can set up some alert. So this is the streaming processing. And what I mean for Potom is really doing something very interesting. That is, we take this to the next level. We also have our storage behind. So you don't have to using your streaming processing to send the data to the other systems such as OLAP or Kafka, but you actually just do everything in our own system alone. We give you the serving layer for both real-time part, but also the historical part. Even you can have a query to query both the historical part and the real-time part. So the keyword like Lambda or Kappa architecture.
Well, we need to get into that. But
yes, that's something we can discuss for sure.
We will dive into that. So is it fair to say that your definition then of a true stream processor is something that's live, it's not very, very fast batch or micro batching, it has to be a continual transformation of a state by a single event?
Yeah, by event, by interval, by other conditions, you name it. But
You define your atom of change, but it has to be sufficiently small to count as true stream processing.
Yeah. We start from those ETL use cases, and we also uniquely design our system to have more historical part, not just rely on the other system to do the historical part. And that's and also we made some design choices to not depend on too many cloud technology, so that we can be easily deployed in those smaller servers, even edge devices or edge or distributed way, so that you can get some data from the local sensors, do some filtering, and aggregate together in a central way. Yeah.
Okay, right. I'm going to get into that, but next, I mean, we're going to unpack this slowly. The thing I find particularly curious about this is you seem to have a dual storage model inside Proton.
That's
so
right.
Take me through that, and especially the why.
Other common choices of stream processing, such as Flink, even I think recently, it's recent 2 or 3 years, the community of Flink also involved, right? They do very good on the computing side. Now they are adding the storage side. So there's a project called Apache Pymon. Originally, it is called Flink Table Store as a sub-project of the Flink. But they realize it's just more than Flink, and they are aiming for much bigger space. They want to create they call stream data warehouse or streaming house, have both the computing side, but also the storage side. And the storage side can be, I'm not saying this is next or the other iceberg, but they really being very ambitious, and they want to support other systems such as Apache Spark. So anyway, why I mentioned this, that is in the Flink community, they move from, or they evolve from a pure computing engine to add the storage part. But in the case of Proton or our company 10 Plus, at the very beginning, we think this is the future. So on the day one, we're not just focusing on a streaming processor on the computing side. We really want to have the vision of, hey, in the future, this should be one single system. People really needed to process data, no matter they're comfortable using streaming way or using the batch way. So we choose ClearHouse as our key foundation, and it's already a very mature batch-based system, OLAP system. We really add extra streaming capability into this core base, so that you can process data in the streaming way, just as a stream processor or stream ETL, very similar to Apache Flink or KSQLDB. But in the same time, the storage, the data is stored in the ClearHouse historical part. So you can query it, say, I want to not just know what is happening right now, but also want to know what is the pattern or trend in the last 2 weeks, 2 months, or even 2 years. It is possible you just query in Proton alone without asking other systems. And also there's other interesting things such as backfill. Backfill is a special term, I think, very popular in the fintech area. That they want to figure out what is my best trading strategy based on those ticks or those stock price or those offers, things like that. Then usually they want to build a good strategy for the real-time part, but also they needed to validate that strategy using the data in the past, I don't know, maybe 1 year or 2 years. They call this backfill. And it is very common. People have 2 teams, one team building this streaming or real-time trading part, the other team building the historical part. Even they can be using different language. So it's at the extra cost and the inconsistency. So in our case, everything is SQL-based, and we are using the same engine. So you can easily build the same code for both the real-time trading and also the backfill test. So there's some benefit to have a system to have both. Yeah.
So this is very much the Lambda architecture that I remember first hearing about at Twitter, where they're dealing with the historical tweet data. I'm not going to call them X's. The tweet data plus the live hot stream of people tweeting right now and wanting to see timelines right now.
Yeah. Lambda, again, is a very popular and relatively easy to understand, but the people also see the challenge of having maybe 2 serving layer, right? 1 serving layer for the real-time part, the other saving layer for the historical part. Even data is saved in 2 different places.
Yeah.
It can be complex, so that's why people come into Kappa architecture. I would say in the case of Proton, it's more like Kappa, but it's more like Kappa in a single binary. So because we have everything written in C++ as our core engine, and it can be compiled to a single binary, and that single binary can serve for both real-time or streaming query, but also the historical query, and all the storage is also unified. So internally we do have historical storage based on ClearHouse. So this is a column-based storage, and it is very fast for you to do aggregation, especially if you don't need to scan all the columns, right? For example, there are 10 or 15 columns. You only want to do min max for 2 columns. The beauty of a column database is that you only get the data part for that 2 columns without getting extra data, and you can apply some SIMD vector processing to get a result in a single CPU core, something like that, without having too many stuff. But so we inherit from ClearHouse, but also in the meantime, we have our own Proton streaming storage. We call it a native log. So it's an internal component, but the purpose of that is all the data is arrived in that streaming storage first. It's more like Red Hat log, apparently. Very similar to Kafka, but much more lightweight. Then the data is there, then we can do some streaming stuff. Then the data also replicated to the historical part so that we can get both the...
So you're saying internally there's a write-ahead Kafka-esque log, which you're querying for the hot set of data and also writing it across to in bundled ClickHouse for classic analytics.
Yeah, that's right. Yeah.
I can begin to see why that architecture has a balance to it, but that sounds like a lot of work on your side to try and... Is it a problem keeping those consistent? Is it a difficult thing to know? How do you know when to query which layer, for instance?
Yeah, that's really an interesting thing we're happy to discuss. So in the streaming world, everything looks very beautiful and easy at the first glance. So that's, of course, why not? But when you really work on that, you might realize there's a lot of challenge. For example, like this out of order, right? So you might get the data from different sensor, you might get from different gateway. They might using different clock, or even certain channel may have some certain delay. So when the data is consolidated into your system, you are not guaranteed that the data will be in the exact same order. Maybe some data arrive first. Yeah, something like that.
Somebody's using a mobile app, but they were on the underground or the subway, and they sent the analytics data like half an hour late.
Yeah. We have some use cases, people using our solution for those fleet management, the sensor on their truck. And if they go into a tunnel, I don't know, maybe it can be 5 minutes, 10 minutes, the signal will be very bad.
Yeah.
So, but they will still try to send out, and you get them late. So there's some out of order event, there's some late event, and also how to keep this state manageable, right? So as I mentioned, that is usually the streaming CQ is running. It's always wrong in the backend, but if you are doing some calculation, it's always add the new data in the state, never reduce. Then no matter how big your memory is, it will be OM eventually, right? So how to have a certain way to control the size of the state, and also stuff like how you can change schema is changed, or how you react when the server scale out or scale down. So there's a lot of challenges. In our case, we do have extra design. One of the key important part of that is we introduce our own format. We call it 10 plus data format, TDF.
Right.
So the TDF is our key data format, have some design to aiming to solve those challenges. For example, we have a column or flag called sequence number. So the sequence number is the important information to let us know, say, when you ingest, for example, 3 data in a single batch to plot them. Then we know each event have ID, and we assign a sequence number. And later on, when there's the other event come in, they have a different or a newer sequence number. Those sequence number, the data will be in our streaming storage first. Then we will keep replicate them to our historical storage, but also keeping that sequence number, so that when we don't really need it to. In some cases, the data can be in both sides, but when we query it, making sure based on that sequence number, we only get the data once. So I give you example, say in our streaming storage, the data, you can set a retention policy for 1 day, for example. Again, this is configurable. In the streaming storage, the retention policy is 1 day. In the historical storage, it can be, say, 1 month. Then in our case, if you wanted to, hey, can you give me the number of events with this condition for the past 1 week? Then we start from our streaming storage and we get 1 day data, and we know it's not enough. Then we can go back to our historical storage to get the data from that one week to that minus 1 day. And because we know this sequence number, so we making sure there's no overlap. So for example, in the stream storage, the sequence number, last number is, say, 500. Then the other one should be 501 or 499, I don't know, but making sure there's very smoothly we can grab data from both sides, but we don't have any duplication. So that's how we can solve those order issues or other issues. Yeah.
So that does sound like there's an extra storage layer in there, because where are you storing that state?
The state today we still save in our native log, which is our streaming storage. Essentially, it's a file-based, but we can replicate to other servers.
So are you kind of snapshotting back to a different write-ahead log?
Yes, yeah. And we have, because it's our own format, we can do a lot of crazy optimization. We have to wait for the community,
Okay, so your system goes down. Let's not say it crashes. It goes down neatly. It comes back up. You're going to then to reserve that query, walk back along the event stream until you find a snapshot, and then add that into the historical. Is that how it works?
Yeah. So for example, we do upgrade. For example, say the version is A, and we need to upgrade to B, and inevitably you have to restart the server, right? So it be just 2 seconds or 2 minutes, whatever. Then we making sure when we start a new server, we pick up where we left. So what's the previous internal state, as well as what's the last sequence number we scanned. So the last sequence number, for example, is 1000. But now in our stream storage, there's 10 more events. We know those new events we never compute. So we can use that sequence number to figure out what's the gap we should process.
Right. Yeah, I'm with you.
Mm-hmm.
Okay. Let me give you another difficult architectural question. So what's your approach with, let's say my fleet of trucks is huge, right? And I'm dealing with, I don't know, what counts as huge these days? Let's say 1 million for sake of argument. I'm dealing with 1 million trucks whose state I would like to calculate over time. How do you deal with when that gets too large to hold in memory? What's your sharding strategy for very large stateful sets?
Yeah, sure. It's not so uncommon, right? So we cannot put everything in memory. I know some database, they really want to put everything in memory, even have some cluster version of a memory-based system. So as you previously mentioned, that is the problem is there. People try to solve in different way, different solution. It's very difficult to have one thing fit for all. Everyone have their own assumption and design choices, or even design preference, or depends on which customer they talk to, right? Some customer hate cloud, some people only use clouds, for example. Yes, in the case of large of state or data, we do have this sharding strategy. I think this is very common. That is, to make it simple, everything is a single shard, but you feel free to design a sharding strategy. For example, you think, maybe 3 shard is enough, or 10 shard is enough. Then it's, sharding, partitioning, those are just acronyms, I think. So you can design a sharding strategy based on certain key, so that data in the same shard is more relevant or similar in some way. Then combining the sharding strategy with the cluster, because you might know even on a single node, a single host, you can have multiple shards, right? So and essentially each shard can be independent I/O. So for example, if you observe that is in your server, the IOPS capacity is very high, you cannot get a higher throughput. For example, you can create more shards so that you can have more in parallel data I/O. So that's the good reason why you might want to have multiple shards even in a single server. But also you want to have some certain HA, high availability or disaster discovery, then you might want to have multiple servers. Then each servers will take different shards, right? So I guess this is quite similar to how Kafka work, right? You can have multiple partition for one topic, and you can have multiple server handle different partition. Even you can have a replication factor. Each partition need to be replicated, let's say, at least twice or 3 times. So combining together, you have a relative common distributed architecture, so support almost any number of events. Depends on whether you have enough disk I/O or disk servers, and the network within them is good.
Yeah. Okay. So that raises another question for me, which is, you've chosen to embed ClickHouse as an OLAP platform, but you haven't chosen to embed Kafka. You've written your own write-ahead log. What's the thinking behind that decision?
We want a system can be deployed as a single binary, as simple as that, or it can be a cluster, as I mentioned. We do support cluster. And even the way how Splunk support cluster, that is, it's also a single binary, but you can run the same binary in different role. Say, I want to run this as a master, I want to run this as an indexer, as a search head. Similarly, in our case, even it's a same binary, but based on the configuration file or based on some lead election, different things can mean different role. And also, because of the single binary story possible, even today, there's a community user in our Slack asking, can I use Kafka to replace native log? And the answer is yes, for sure.
Okay.
So we made this as a more like interface. That is, we need a stream storage, and we have our own one we call native log. It's part of our process. But if you really want to configure external message bus such as Kafka or even Rapanda, you can do so. Then we just leverage this as a streaming storage for put our write-ahead log or put our TDF format. Okay, so that is configurable.
So that state snapshot you're talking about, that could be written to Redpanda instead.
Yeah, that's right. That's the data part. But also, besides the data, there's also other, for example, metadata information, how you define things like materialized view, how you define a stream, and do you create the stream on this node, how other nodes are aware of that, right? So those information, we call metadata information, is, I think today is still stored in the file format. And we replicate to other node using the Raft protocol. So again, internally, there can be some data in the streaming storage, some data in the historical storage, some metadata information in the form of file, and the file can be replicated to each other. Yeah.
Okay. That makes me want to talk about, because you've talked about how this is embedded, how there's a trade-off between the historical and the real-time stuff. Makes me want to think a bit about performance. Like what kind of queries does it perform really well on? What kind of size can you optimize for this kind of hybrid internal architecture?
Yes, performance is really one of the key kind of driving factor when we design things. We have some of the similarity with Rapanda. For example, Rapanda basically is a C++ version of Kafka, right?
Yeah.
And
I think that's a fair summary.
in some oversimplified way, Proton is a C++ version of Flink, or we call it a native engine of Flink. You know what is happening interesting right now? That is, there's some native engine for Spark. Spark is written mainly in Java, some part written in Scala.
Right.
But in some use cases, people are not very impressed for the performance of Spark, the Java version, JVM version. So there's a few projects coming from Facebook, coming from even Apple, I think. They are written this in either C++ or Rust as a native engine for that. Even, the company behind the Spark, Databricks, they have been building this for 4 or 5 years and use this for at least 3 years. They call it, I don't know how to pronounce it. It's a Photon. It's Phton. It's very similar to Proton, but with the letter H. So that is a native engine. I'm not sure whether it's Rust or C++, but it's a in-place replacement for Spark. So you can run your Spark workload, but it's executed using the engine. So you see people, if really want to aiming for the next level of performance, JVM may give you something, but may give you some limit, right? If you want to leverage SMD, you want to leverage vector computing, you want to have some modern file system, IOU ring, the memory management, those stuff. You might have to do this manually. Yeah.
Java is vastly faster than it was when it first came out. It's incredibly fast, but if you want to have an argument with the CPU directly, you kind of need Rust or C++ or C. Yeah, I can see that.
I even see some folks, they are tuning for ARM. There's a lot of details. If you do this carefully, you can get way more faster, but it is underestimated. So, a lot of programs should run faster on ARM if they do properly, but they require a lot of effort. But anyway, long story short, that is, we choose C++ as our language to implement. We leverage a lot of high-performance C++ library. We always use the latest C-Long, LLVM, all those cool things. So we can get a very, very low latency without require a lot of computing resource. I'll give you an example. For example, one of our community user, they need to do, they call high cardinality group by. The term is fancy, but essentially it's just a group by, in the SQL group by key, right? But what if the key is not 1,000, maybe say 10 million? So imagine you have 10 million unique key, and each key you need to get a certain aggregation, for example, the count, the min-max, or even some crazy one like a P99. All right, so if you want to do the extreme case, that is you have a 10 million unique key, each key you need to do some P99. P99 is tricky because you need to get all the data and figure out which value is at the 99%. Right, so it's more complicated than sum or average. Yeah. So, but in such cases, many systems cannot handle that. But because we implement in C++, we have our own control for the data structure. We can actually spin off multiple internal process to leverage the modern CPU and all the Linux stuff to get this result correctly without have a lot of memory. I think, I don't remember the details. I think it's more like 4x or even 10x less memory compared to Flink for the same high cardinality group by. And this is, high cardinality group by is very common for some use cases such as cybersecurity. You may know, for example, if you have firewall access log, you want to figure out which IP keep sending you some package, and the IP can be easily a large number of, so it's high quality. And some other cases, such as a fintech, you might have a lot of stock or Bitcoin, things like that.
Yeah,
so
especially if you go into like IPv6 grouping by that. Yeah, that's big.
I'm not saying it's a nightmare, but it's a really big challenge.
Yeah. How is that? What's you're saying you can get 4x or whatever out of that? What's the key part of that? What's the thing really making the difference?
Yeah, I would say it's really, we can leverage the low-level CPU or IO or Linux stuff. And I think Flink, in many ways, it's designed in a very generic way. And we also, with some limitation of a JVM, you might have to do certain things in a generic way. But when you have the chance to handle things, I give you a very simple example. For example, as simple as this a bunch of integer.
Yeah.
Right. So again, I haven't written C++ for a long time, but if you design your data format in the proper way, for example, every integer is, for example, 2 bytes or 4 bytes, you make this as a fixed width, and using the same representation as the memory, then essentially it's just more like a memory dump. You do the minimal Marshall and Marshall things. I guess this is also similar idea as Apache Arrow, right? They have the memory representation of the memory in the network, in the disk. So same thing, that is, if you do this in a careful enough way, you are handling data package in a very efficient way. I'm not quite sure whether you can do this easily using Java.
Yeah. I'm gonna say you can't. I don't think you can do it easily. I'm sure someone will tell me that you can do it, but it doesn't sound like it's a natural fit for a virtual machine that tries to abstract away from these things. Someone will educate us both on that one. But okay, so you've mentioned this a couple of times, and while we're talking about architecture, I have to ask this. If you're talking about ARM and embedded systems you've mentioned, is this, if I were to stick a Raspberry Pi out in a field gathering interesting data, is this a good choice for that?
Yeah, it can be. So at earlier days, I use, I forgot what's the instance type name. It's T2 Nano. It's a very small instance on AWS. I guess it's half CPU, 1 gigabyte memory.
Okay.
I used that for a long time for my demo. Yeah, because our binary is still so small. It's a few hundred megabytes. It can be even smaller. But what is nice that is if you just run some filtering or some bounded tumble window, so it just process data constantly and send data back to Kafka, for example, then it don't really require a lot of memory. So don't want to pick up on Flink, but just as a standard, that is, you want to set up a Flink, you need to have the right version of JVM. There are so many different JVM versions. Different vendor want to have certain control on the JVM. Anyway, you choose the JVM and you download Flink. Maybe you put in a certain path, you start it, then you say, yeah, cool, I want to get data from Kafka. And you copy the SQL from the documentation and run it. It show you a result that it class not found. And then you figure out, oh, I need to download the Kafka jar file somewhere and put it into the library. Then you restart your server.
Literally done this.
Yeah, then you run this and you want to, oh, maybe I need to create a jar file and deploy that jar file as my custom code. So, I mean, and the server require a certain amount of CPU and memory. I know there's certain way you can customize your Flink to consume less data, but it's not default. So my point that is, again, Flink is already a great product, but you still need to figure out on many details. But in the case of Proton, because we are so focusing on the simplicity, you just run a single command to download as a single binary or have a very small Docker image, and it can connect to your Kafka immediately. And we are using the librt Kafka, I mean the C++ library from Kafka, so it can connect to Kafka and to read or write. And I think it's fairly easy to support, for example, the resource on the Raspberry Pi. We also support ARM for a long time because we have multiple cluster, and some of the cluster is based on the ARM chip, Amazon Graviton. Yes, Amazon have a very nice ARM-based chip with as up to, what's the number, up to 30% discount or something like that. So it's much cheaper than the AMD or x64 chip. So we use that for a lot of our internal tests. So there's there's some difference, but not huge. So if you really want to run stream processing on your Raspberry Pi, on your embedded device, I think Proton is almost the best choices. Even Rapanda is doing something similar. Might be possible to run Kafka in your Hermit, in your other device, but it's much easier you run Rapanda in those small devices, and you can maybe put Proton there to do some SQL-based stream processing.
Okay, yeah, because that seems like fun to me, to be able to do the processing as well as the storage all in one simple place.
Yeah, and one more thing to add that is we even talk to some of the users. For example, they are in the energy space. They needed to get the oil, and they have a lot of sites, because sometimes it's just like lucky draw. You put a lot of stuff there and figure out among those 3,000 sites, which one have a lot of oil behind. So you need to have a lot of sensor. And those are remote space. You don't really have good enough network. Even you apply like 4G, 5G, it's very expensive.
Yeah.
So the solution is more like you have a lot of more like local data center or micro data center, and you get the data, you do some filtering, processing. You might be able to consolidate them into the central servers one day, but if you can solve those distributed environment network air gap, but if you can apply stream processing or real-time processing, they can filter out a lot of garbage data and figure out what's the real signal and help you to figure out which well you should spend more money on.
Because those kind of in-field processors tend to pick up a lot of noise along with the signal. If you could pre-process that in the field, that makes sense.
Yeah.
Do you think there'll be, or maybe there is already, a way in the architecture to then say, okay, so I've got this Proton node which has filtered out some of the uninteresting data, but still got a lot of interesting data. Can I now sync that back into my mothership cluster when the connection comes up?
Yeah, it's already ready, right? So this is our design goal. That is, each node is, I'm not saying self-driving, but they can do everything by themselves. Do some filtering, figure out those information that interesting stuff. Then they can send them to a central server when they detect the network is good.
Okay,
right? So
cool.
because we have some storage or like buffer, right? So you never lose data. But when the network is recovered, or when you turn on the network, then that kind of data can be synced to the central server. The central server can know all the data around different sites and do some maybe correlation search or pattern detection. Yeah, okay. So it's pretty much like Kafka or the mirror thing. It's similar to that, but
like Mirror Maker.
So we just implement this in the Proton side.
Okay. So come the day that Amazon have their drones flying around us in the sky, you'll be hoping they've embedded a Proton server in each one.
I hope there's many choices, but assume they have a good like 4G, 5G, so they can generate the data and send back to a server. I guess some users really want to do everything locally.
Yeah.
But if the network or latency is okay, I think having each sensor on the drone sent to central Kinesis or Kafka do the processing there will be easier. I mean, we don't have to looking for trouble, but there's a lot of choices for sure.
That would be interesting trouble to get into.
Yes.
And then you'll have to optimize your binary for the weight.
Yes. Yeah.
If someone wanted to kick the tires on Proton, where do we go first?
Yeah, of course. Yeah, go to our repository on the GitHub. You can also get this from our timepass.com. That will be easier. You just go to timepass.com. I think we have a big enough icon to guide you to our GitHub. And in our repository, there's a command line. It has many options. Right? You can have using CURL to grab our binary from our server, and you can run this directly, or you can install it. I mean, install it just meaning you install to a certain path and with some configuration file, but it's optional. You can just run that binary in your current folder. So everything is very easy. And also we have Docker image. Besides that, we have a bunch of Docker Compose. So Docker Compose is really a good way to create some sample stuff, right? For example, we have a sample how to using Panda to generate some data about the clickstream and visualize using, for example, Grafana, right? I mean, because I mentioned we have not just a stream processor, but also a serving layer. So that's something, if you are somehow no Flink, I don't think that's easily you can do, that is using Grafana to visualize your Flink query. Because Flink essentially want to get the data, process it, maybe send to a Kafka or send to OLAP. Then you can query from there. I mean, Flink is not really designed as a serving layer. Maybe they have something like Gateway recently, but it's not.
I gather it's trying to just do transformation and not do storage or serving.
Yeah. So you might have to send data to ClearHouse, then using Grafana or other BI tool to query it. But in our case of Proton, you can just using Grafana to query Proton directly, showing nice charts. Yeah. Grafana, Metabase, Redash will all support them. Yeah.
How's that working? Are you just embedding a web server in it and Grafana is going to there, or is it going, have you got some native connector?
Yes, that's also, we largely leverage ClearHouse, right? So we, Proton is, we call powered by ClearHouse. It's not really running a separate ClearHouse process in our stuff, because there's only one process is called Proton if you choose the single node way.
Right.
So it's entire thing, Proton is a process. Then we just have this a lot of nice thing from ClearHouse, and including this port, right? So for example, ClearHouse supports, it's interesting. People in ClearHouse are really focusing a lot on the simplicity and the flexibility. So they have HTTP port, they have a TCP port, they even have different port for different database. For example, you can turn on certain ports to using Postgres or MySQL client to connect to ClearHouse. It is possible.
Oh, really? I didn't know that.
So those stuff we get almost for free, right? So because Proton leverage that, so we really customize the ClearHouse Grafana plugin so that it can have much better integration with Proton. But that kind of a channel, that TCP, HTTP, all those stuff is largely inherited from ClearHouse. So that's the reason why we really get a lot of benefit from ClearHouse. All those nice different driver for different language. We have integration for BI systems, but also we are contributing back to the ClearHouse. For example, we contribute some PR regarding how we do streaming processing back to the community, so that if ClearHouse team want to merge it, then you can get some basic stream processing in the official ClearHouse version. But if you want more features, for sure, Proton will be the best way. But in the same time, Proton, because we are a small team, we can iterate, try different things faster, and we willing to share all the stuff to ClearHouse team, but they might be more focusing on, I don't know, maybe data warehouse market as a primary goal for them. Streaming is something you want to do, but willing to us as contributor, but they may don't have enough team focusing on the stream a lot in today.
Yeah. Here's the code. Do with it what you will. That kind of thing. Yeah. Okay. Well, I'm going to go and play with that then, because I have installed and tried Proton, but I didn't know I could connect Grafana to it and get nice, pretty graphs for free. So I'm going to go and do that. Jove, thanks very much for joining me.
Thank you.
Thank you, Jove. Thanks for listening.